Okay, so for this next problem, this is problem 6. I'm assuming you've already watched the part 1 video. Okay, so we're doing problem 6 from the section. So remember, watch the part 1 video if you have not watched it already. Okay, very important. Now, how would I begin this? I mean, can I factor it like this? Can I just start doing this? You could if it was quadratic, and you could try to piece it together, but it's not quadratic, it's third power, right? So that's not going to work. So instead, we begin with the rational zeros theorem. So the potential rational zeros are going to be in the following list. It's going to be the factors of the constant term. The constant term is 20. What are the factors of 20? Plus or minus 1, plus or minus 2. 4 goes in, right? 5 goes in. It's not 6, not 7, not 8, not 10 goes in, right? And then 20. Okay, over the factors of the leading coefficient. So 25 is plus or minus 1, plus or minus 5, and plus or minus 25. Now we're going to have a lot of combos, right? We're going to have 1 over 1, 1 over 5, 1 over 25. So you're going to have plus 1, you're going to have positive 1 over 1. So we're going to have plus or minus essentially 1 over 1, which is 1. You're going to have plus or minus 1/5. You're going to have plus or minus 1/25. You're going to have plus or minus 2 over 1. You're going to have plus or minus 2 over 5. You're going to have plus or minus 2 over 25. And that's going to go on, right? I mean, this is a long list. I don't like it. You like it? I don't like it. So I'm going to gamble. You like to gamble? I'm going to gamble, okay? First of all, let's go ahead and get out of this. We're in a table for the previous problem, so I'm going to hit second function, quit to get out of table mode. I'm going to go ahead and put my function in. So let's clear out the old function from the last problem, from part 1. Let's put in this new function, 25, and I'll show you how we're going to gamble. 25x cubed. So the rational zeros theorem will give us a list of all the possible rational zeros, but it takes us a long time just to write out the list. And then we have to check them all, which is also going to take a long time. So I'm going to gamble. Now, when you do the minus 140, just use the subtraction operation, which is here. Do not use the negative symbol. That's just for negative numbers. Okay, so minus 140, x to the 2. So for x to the 2, you can just use this x squared button, save a little time. And then plus 71x. And then plus 20. Okay, so I've got the polynomial in there. So now what I'm going to do is, watch this. I'm going to go to table set. And I don't want to type in numbers because I don't want to have to check this list. If I wanted to check this list one by one, I would leave it on ask for the independent. Okay? I don't want to do that. So I want to just generate a table without having to type all that stuff in. So I'm going to go to automatic. Okay, I'm also going to start the table at 0. Just a convenient place to start. And make sure the delta table is 1. That way I'm going to move by 1 unit every time, which means I'm plugging in whole numbers. Okay? Delta table is how much each row moves by. Each row, if you make it move by 1, that means you're using whole numbers. Okay? Now let's just generate the table. Second function table. I already see a 0. Boom, right there. Okay? At x equals 5, I've got a 0. How do I know? You plug in 5. The table's telling you you have a 0. I just saved a lot of time, didn't I? Like a lot. All right? So I already have a 0. Now, by the way, if suppose I didn't get a list, like I'd scroll up and down in this list and look for something, an x value that gives you 0. If I didn't find one, then what I might do is I'd notice, okay, the denominator also possibly is 5. So then I could go to table set and make my delta table 1/5. So I move by fifths. 1 divided by 5. If you do that, which is, it's going to convert it to a 0.2, but that's the same thing. Okay. Now if I generate a table, it's going to move by 1/5. This is 1/5, 2/5, 3/5, 4/5, 5/5. 6 over 5, 7 over 5, 8 over 5, 9 over 5, 10 over 5, etc. Now I'm moving by 1/5. Okay, oh, I found another 0. Look at that. 1/5, 2/5, 3/5. I found 4/5 is a 0. Okay, so notice that if you initially just put whole numbers in, so if I make my delta table into 1, always start at 0, make your delta table 1, and make a table. Scroll up and down to your table. If you find a number that makes the polynomial 0, that means you found a whole number, because these are whole numbers. So I already found that x, so I'm going to erase this. So I have more room here. So what I found is I found that x equals 5 is a rational 0. Okay, that's really all I need, because once I found that, then I can do this, and I can say, okay, that means x take away the 5 is a factor. Right? If x equals 5 is a 0 of the function, it makes the function 0, then x minus that quantity is a factor. Now, if that's a factor, then I just do a division. X minus 5, I want to pull that factor out of the polynomial and see what's left over. 25x cubed minus 140x squared plus 71x plus 20. So how do you make an x become a 25x cubed? How do you make the first term match the first term? I need a 25, because that's a 1. And then I need 2 more powers of x. Okay? When I multiply back down, what do I get? 25 times 1 is 25. X squared times x is x cubed. Now 25x squared times 5 is just going to become negative 125 times negative 5 is negative 125x squared. Like that. Subtract. Okay, and what do we end up with? 25, take away 25 is gone. Negative 140 plus 125, because minus on a minus is plus, leaves me with what? Negative 15x squared plus 71x plus 20. Okay, how do I make an x look like a negative 15x squared? I need a negative 15. Okay, negative 15, and then I need another power of x. So I'm going to have negative 15x squared, and that's going to be what? Plus 75x. Subtract, because it's been accounted for. Negative 15 plus 15 is gone. 71 minus 75 is negative 4x. To make an x look like a negative 4x, I can just go negative 4. Negative 4 times x is negative 4x. Negative 4 times negative 5 is plus 20. Subtract. Remainder is 0. We're happy, right? Which means this, we did the factorization. We do have indeed a factor. So that means I now have that this polynomial is x minus 5 times 25x squared minus 15x minus 4. Okay, now how do I factor the rest of this? Well, if you're good at factoring by hand, or even moderate at factoring by hand, it shouldn't be that bad. I would probably break this up. I'd probably try a 5x and a 5x, because 25 and 1 is going to be too extreme. It usually results in really big numbers. So I'll try a 5x and a 5x, and then for the 4, we can either try a 4 and a 1 or a 2 and a 2. Okay? If I try a 2 and a 2, you'd have to have one positive and one negative 2. And that's going to end up with zeros in the middle, because you'd end up with plus 10x and minus 10x. So let's try a 4 and a 1. And we want more negatives than positives, because I want a negative in the middle. So I'll try minus 4 and plus 1, see if that works. So I'm going to check this with FOIL. You ready? Let's FOIL it and make sure. Okay, so we're going to have 5 times 5, 25x squared. That's the F of FOIL. Plus 5x minus 4x. I'm sorry, minus 20x. What am I doing? Minus 20x. Sorry about that. Okay, that's the I of FOIL. And then last times last is minus 4. Right, that's the L. So I've got 25x squared minus 15x squared, right, because this combines to minus 15. I'm sorry, minus 15x, not x squared. So 25x squared minus 15x minus 4. So that does work. The FOIL works. So this is the correct factorization. So we're done, right? We found the factors, right? My factors are right here. Just put the x minus 5 into there, and there's my factors. Bada boom. Okay? You could also do bada bing if you like. Now, if we look back at the rational zeros theorem, remember, if my factorization is x minus 5, 5x minus 4, and 5x plus 1, what are the actual rational zeros of the function? Well, if I set x minus 5 equal to 0, I get x equals 5. If I set 5x minus 4 equal to 0, I get x equals 4 over 5, right? Add the 4 and then divide by the 5, 4/5. That was in my list if you look back at the list. Okay, and then here I would get 5x plus 1 is 0, so I get x equals negative 1 over 5. Okay, so these are the zeros. These were all in that list of potential, rational zeros. It's just that it was a huge list and I didn't want to have to deal with it. So I gambled that I was going to get a whole number 0. Did we get a whole number 0? Yes, we got a whole number that serves as a 0, the 5 does, and that started us off. Once I knew x equals 5 was a 0, I knew x minus 5 was a factor. Once I knew x minus 5 was a factor, I could divide it into the polynomial and see what the remaining factor was. That remaining factor still has a power. So I factored it by hand. Luckily, it factored by hand. I did not need quadratic formula. If I did, I would have had to use quadratic formula. Okay? And there we go. Fun, 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 right? Wait, let me check that. Let me Google it. On my other screen here, I'm Googling it. And yep, it says this is fun. I just checked it. Okay, yep, that's what it says. I'm not kidding. All right, so let's go on to the next problem. Okay, so here I am at an example of problem number 7 on the homework. Again, we want to factor this. To factor it, we start off life with the rationals, so my potential rational zeros. Okay, that says rational, it looks kind of funny, but potential rational zeros are going to be, well, let's see, factors of 15, factors of the constant term, divided by factors of the leading coefficient. Well, the 15 is what goes into that? Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Okay, how about on the bottom? The 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. This doesn't look fun. Why? What are my potential rational zeros? 1 over 1, 1 over 2, 1 over 3, 1 over 6. 3 over 1, 3 over 2, 3 over 3, 3 over 6. 5 over 1, 5 over 2, 5 over 3, 5 over 6. And again, plus or minus of all of those. 15 over 1, 15 over 2, 15 over 3, 15 over 6. Not fun. How much fun? Answer, not fun. Okay? So in this case, instead of plugging away, I'm going to gamble. How do I gamble? I'm going to gamble that there's a whole number 0. Okay? So first let's quit the table mode from before. So second function, quit to get out of table mode. Let's go to y equals, clear out the old function. Let's put in this new guy. So I got 6x power 3, go to the right to get out of the power, plus 5x to the 2, minus 34x, plus 15. Boom. Okay. Let's go to table set. Make sure that I'm starting at 0 and that my delta table is 1. When I make my delta table 1, that means I'm going to plug in whole numbers. Make sure it's on auto, because I don't want to have to type in this whole list of a whole bunch of things. I want to just gamble that when this generates a table with whole numbers, it'll hit a number that makes a 0. Okay? I'm gambling. All right? I might win, I might lose. Okay, so let's go ahead and make a table. So second function, table. And let's see, I don't see a 0 there. But wait, I'm only looking in the positives. Let's look at some negatives. Ding, 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 ding. You see it? Right there? Look at that. Right, you hear that bell go off? Ding, 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 ding. There it is again. Okay, negative 3 is a 0. Negative 3 results in a 0. Okay, so I already know x equals negative 3 is a 0. Okay, that means I have a factor of what? X take away negative 3, which of course can be rewritten as what? X plus 3. Okay, so I already know that's a factor. X plus 3 is a factor because negative 3 was a 0. So now let's pull that factor out and see what's left. Okay, so let me erase here. And let's go ahead and divide in. Okay, so I'm going to take x plus 3 and divide it into the polynomial. 6x squared, or 6x cubed, I'm sorry, plus 5x squared, minus 34x plus 15. Now, is factoring and finding zeros always this hard? The answer is pretty much yeah. It's one of the hardest things in mathematics. In fact, factoring polynomials is so difficult. If you look up how encryption works on the internet, like when you enter your credit card number and it somehow gets the other side with nobody intercepting it, the way that works is basically through the fact that polynomials are extremely hard to factor. Okay, if you kind of look into encryption, it uses the factoring property because factoring is so difficult. Factoring is difficult stuff. That's just how the world is built. Okay, now, how do I make the first term on the outside look like the first term on the inside? And the answer is, I need a 6, because 6 times a 1 is a 6, and I need 2 more x's, 2 more powers of x. Okay, so I'm going to get what? 6x squared gives me what? 6x cubed plus 18x squared. Okay, subtract. What do we end up with? We end up with 6x squared, 6x cubed, take away 6x cubed is gone. 5 of these guys, take away 18 of them, gives me what? Negative 13 on those x squareds. Or you could, of course, change the signs and add. And then negative 34x plus 15. How do I make a 1x look like a negative 13x squared? And the answer is, I need what? I need a negative 13 and an additional power of x. Multiply back down, negative 13x squared, negative 39x, subtract, because we've accounted for all that. Negative 13 plus 13 is gone. Negative 34 of these guys plus 39 leaves me with 5 of them. How do I make an x look like a 5x? And the answer is I need a plus 5. I need to multiply by a positive 5. 5 times 1 is 5x, just plain old 5x, plus 15. And I can see right away that it's something minus itself, right? And so the result's going to be 0. So we did get the remainder 0, which means the factorization, this was indeed a factor. So that means this polynomial is what? X plus 3 times 6x squared minus 13x plus 15. Plus 5, I'm sorry. Right? Now, how do I factor that further? Hopefully it factors by hand. Otherwise, we'll have to use quadratic formula like we did a couple problems back in the part 1 video. Okay? So I'm going to try, let's see, should we try 6x and 1x or 3x, 2x? I'll probably try, I usually like to try the smaller numbers first, so 3x, 2x. And then for 5, you only have a choice of 5 and 1. So if I put a minus 5 here, the minus 5 would hit the 3, make minus 15. And I can put the 1 here and make a positive 2, so that'll work. So if I go minus 5 and plus 2, plus 1, I'm going to have, if we FOIL this, let's just check it with FOIL real quick. Okay, so first times first, 6x squared, right? Then outer times outer is minus 15x. Inner times inner is plus 2x. Last times last is minus 5. So I have 6x squared minus 13x minus, we end up with a minus 5. Did I goof up? Looks like I goofed up, right? Let's try switching them, okay? Sometimes you goof up, especially when you're recording at 3:30 in the morning. Okay, no joke. Okay, so let's go ahead and switch them. Okay, so life's fun sometimes. So let's try 3x minus 5 and 2x minus 1. Let's try that. Let's try foiling it and see if it works. Okay, so 3x times 2x is 6x squared. Outer times outer is minus 3x. Inner times inner is plus 10x. Minus 10x, inner times inner. And then last times last is plus 5. So if I add up my like terms, we're going to have what? 6x squared minus 13x plus 5. So that is, that's working, right? That matches this. So that means this was the factorization. So my final set of factors here is going to be what? x plus 3, and then these guys, 3x minus 5, and 2x minus 1. Okay, that's it. That's my factors. Whoops, that's here. I'm sorry. That is, that's the factors. That's this. This part just wants the zeros. So what are the zeros? Whatever makes the factor 0 are the zeros, right? So my zeros are going to be, so if my factors are x plus 3, 3x minus 5, and 2x minus 1 are my 2x minus 1 are my factors, then set each one equal to 0 to get the zeros, right? 3x minus 5 is 0, so x equals 5/3, and then 2x minus 1 is 0, so x equals 1/2. Okay, so I would have -3, 5/3, and 1/2. Okay, fun, right? I'm not even going to Google that because I know it is fun. Okay, all right, let's try another one. Okay, so here's problem number 8, and I already don't like the looks of it. Why? Because it's telling me, ooh, there might be irrational zeros with radicals. Fun. Okay, so we got to be careful here. That we expect this to not be that pretty. So, but again, we're going to begin life with the rational zeros theorem. So my potential rational zeros of this function would be factors of 35, factors of the constant term, divided by factors of the leading coefficient. So factors of 35 would be what? Plus or minus 1, plus or minus 5. 7 times 5 is 35, right? So plus or minus 7 and plus or minus 35 divided by factors of a 1, leading coefficients of 1. That's good because that means there's not a lot of combos. So it's 1 over 1, 5 over 1, 7 over 1, or 35 over 1, right? So I'm going to have 1 over 1, which is just 1, 5 over, and plus or minus. 5 over 1 is just 5. 7 over 1 is just 7. And then 35 over 1 is just 35. So I only have 1, 2, 3, 4, and then the negatives. I only have 8 numbers. That's not too bad to type in. So I'll just, now notice they're all whole numbers. So I could either type them in, or I could just generate a list again in my calculator using whole numbers, and these will be in the list. Okay, that's probably faster than typing them in. So I'm just going to go to quit, go to y equals, clear it out, put in the new polynomial. So I have x cubed. Do you have to say it funny like that? No, but you can. Okay, x cubed plus 11x squared plus 37x. Oh, I got the sounds turned on. 37x and plus 35. Okay, there's my poly. Now let's make a table. So first table set, make sure my settings are correct. I'm going to start at 0 and go by ones. That means I'm plugging in whole numbers. That's good because I get whole number possible zeros anyway. And so now I'm going to generate the table. And I'm looking for something that makes it 0. So far I'm striking out here. But I need to also look up at, now it's unusual if you have to go all the way to the biggest number to get a 0. That's unusual. I'm going to just go into the negatives here a little bit and see if I spot a 0. There we go. I've spotted a 0. Okay, right there at -5. Okay, and that's in my list, right here. It's +5 or -5 are both in my list. So therefore, I already found x equals -5 as a 0. There might be some more in this list, but that are actual zeros, but actually they weren't, right? They weren't there. We could scroll down to plus or minus 35. It's also not going to work, okay? Because these numbers are becoming huge already. So so it looks like the only rational 0 was a -5. I mean, if you want to, you could plug in 35 and -35, right? I can go table set, go to ask on my independent so I can type stuff in. And now I could type in 35 into my polynomial like we expected, and I can try -35. Super bad, right? The 5 works though, right? 5 didn't work. but negative 5 did. Right? 7 did not work. Negative 7 did not work. But we already found our 0, right? Negative 5 is our 0. So, so if negative 5 is our 0, that means x plus 5 is the factor, right? So if x equals negative 5 is the 0, that means x minus the negative 5 is a factor. And we could write that as x plus 5 as a factor. Okay, so now let's do our division. I know, wow, lots of division, but hey, that's part of life, okay? So we're going to divide x plus 5 into the polynomial. If you're a, you could also apply synthetic if you want, but I just always do long division so I don't have to worry about whether I'm in the right case or not. Plus, it's good to just get really good at long division, okay? X cubed plus 11x squared plus 37x plus 35. Okay, let's divide in. So I'm going to have x into x cubed. The numbers out front match 1 and 1, so I'm going to have an x squared. X squared times x cubed, 5x squared, right? Multiply back down, subtract, and we end up with now x cubed, take away x cubed is gone. 11x squared, take away 5x squared, it leaves me 6x squared. Or you could always change it to addition and change the two signs. Okay, and now I'm going to say, okay, how do I make an x look like a 6x squared? I need a plus 6 and another x. 6x times x, 6x squared. 6x times 5 is 30x. Subtract. That's gone. 37x take away 30x is 7x. Okay, how do I make an x look like a 7x? I go multiply it by 7. So I get 7x plus 35, right, because the 7 times the 5. Subtract, and I get my good old buddy Mr. 0, which I like very much, right? That's supposed to be a smiley face, a scary looking smiley. Okay, so that means that my polynomial already can be written as what? I can write this guy as x plus 5 times, let's see, we've got x squared plus 6x plus 7. Okay, now if I try and factor this by hand, let's see if it works by hand. We expect it's not going to. Why? Because they're already kind of warning me I'm going to end up with irrational zeros. If this worked by hand, if you can factor it by hand, then you're going to get rational number zeros. So they're already kind of warning me it's not going to work. But let's try it. The only way to make a 7 is either minus 7 minus 1 or plus 7 plus 1. So either plus 7 plus 1. The middle term would be 7x and 1x makes 8x, doesn't work. Or x minus 7, x minus 1, which would be minus 7x and minus 1x makes minus 8x. So neither of these work, which means we do have to use quadratic formula. Okay, so let me make some room here. Okay, so we had x squared plus 6x plus 7 was the result of the division. And then we were dividing in the x plus 5. So this was our initial factorization. That's not a complete factorization because I still have powers. Okay, but now we can factor this remaining quadratic factor by using quadratic formula. So my a is 1, my b is 6, my c is 7. Okay, when I find the quadratic formula, will find what makes this polynomial equal to 0, and then x minus each of those would be factors. Okay, so my x is going to equal negative of the b coefficient plus or minus square root of the b squared minus 4 times the a times the c, whole thing divided by 2 times the a. So that's going to be negative 6 plus or minus, let's see, 36 take away 28 is 8, so root 8 all over 2. Now root 8, as we said before, and 8 really factors as what? 2 times 4, and the 4 fact, that's done, and the 4 is really 2 times 2. So really 8, so root 8 is the same thing as root of what? 2 times 2 times 2. And so we can, anytime you have a pair of things inside of a square root, you can cross them out, put one on the outside. So I have 2 root 2. So I have negative 6 plus or minus 2 root 2 over 2. And now what do I do? Well, can I cancel these 2's? And we've talked about this before, and the answer is no. Anytime something's adding or subtracting to something else, you cannot cancel it. That's the biggest mistake in algebra. Okay, instead, we factor out a 2. Negative 6, if I factor a 2 away from it, negative 6 divided by 2 leaves me negative 3. If I pull the 2 away from 2 root 2, the 2's been pulled out, I'm just left with the root 2. These do cancel because neither one is adding or subtracting. This one's only multiplying, and this has nothing else with it. Okay, so those do cancel. So I end up with negative 3 plus root 2 and negative 3 minus root 2 as my two solutions to the quadratic. So therefore, what's my factorization? Right? This is should be an old story by now. My full factorization is going to be x plus 5. So technically x minus negative 5, because negative 5 was my 0. X take away negative 5 times x take away negative 3, x take away negative 3 plus root 2, and then x take away parentheses negative 3 minus root 2. So that's my full factorization, but not very pretty because I have multiple parentheses everywhere. So how do I write it without multiple parentheses? It's going to be x plus 5 times x minus a negative 3, right? That distributes in, so it becomes plus 3, and then this distributes, so minus root 2. And then same thing, that's going to become plus 3. So x plus 3, and then minus on a minus becomes plus root 2. Okay, so this would be our factored form. Okay, fun, right? Wait, let me check it. Yep, I just Googled it on my other computer, and indeed it came up with fun. Okay, actually it came up with lots of fun. Okay, but that's still fun. All right, so let's go ahead and pause this part, and we'll go to a new part in the recording.